All right, so it's now, of course, been very well established that the avian respiratory system consists of a pair of small rigid lungs that are connected to an elaborate system of air sacs that run throughout the body. Large regional air sacs give rise to lots of smaller, complex branches that are referred to as diverticula. And some of these diverticula anastomose around the vertebrae. So some have even been given names. Common ones that I'll be referring to occasionally throughout the talk include the intertransverse canals. These are bilateral diverticula that run on either side of the vertebrae, and sometimes these will anastomose with supravertebral diverticula. Sometimes the supravertebral diverticula are just on top of the vertebrae and don't anastomose with the intertransverse canals. But what gets even weirder is that these diverticula don't only anastomose around the outside of the vertebra, they also will anastomose and enter the vertebral canal itself and contact the spinal cord. And this forms structures that have been known as supramedullary diverticula. So it's super weird because inside of at least some parts of the vertebral canal in birds, the spinal cord's not occupying that entire space. It's also occupied by air from the diverticula. Here you're seeing the diverticula, those black spaces, in a fresh dissection of an ostrich neck. And I'll talk more about pointing them out in a second. So they have been thus far described as diverticula that branch from the lungs and the air sacs that are inside of the vertebral canal and that are in contact above the spinal cord. At this time, I'd like to introduce a color scheme I'll be using throughout the talk to help your eye quickly be able to see the structures that I'm discussing. So the vertebral canal will always be in yellow, the spinal cord will be in magenta, and the supramedullary airways themselves will be in teal. What's also neat about these structures is that they're very easy to spot on CT scans, since they are literally just black space above the soft tissue spinal cord. So the results you're seeing from my study I'm presenting today have all been collected from CT scans. Prior to this research, only 4 other publications have mentioned supramedullary airways. Oh, also another side note on terminology, I use supramedullary airways and diverticula synonymously. Airways is a little bit less of a mouthful, but I mean the same thing. 4 prior publications have mentioned these structures, but of the 4, only 2 have described them in any detail. So really, to date, that means we only know about supramedullary airways in 2 taxa from 2 major clades, in pigeons and in turkeys. This study has brought that number up to 26 genera, representing 18 different major clades. So we've really been able to expand our knowledge of these structures to much greater phylogenetic coverage. The first thing we noticed was that the vast majority of birds do have these structures, everything ranging from ostriches to hummingbirds to exotic taxa like psittaciforms, parrots have supramedullary airways. Lots and lots of birds have them. But there were a handful that did not. Loons and grebes don't have supramedullary airways, and neither did either of the pisiforms in our data set, which were both woodpeckers. In the case of loons and grebes, this isn't terribly surprising. They're both pursuit divers, so they're spending a fair amount of time underwater when they're hunting, and it's been well documented that they have reduced skeletal pneumaticity as an adaptation to this. But that functional explanation doesn't help us understand why pisiforms might perhaps lack supramedullary airways. And furthermore, when we went back and looked at our data set and got over our initial assumption about this perhaps being adaptive, we realized we actually had 2 birds that are also pursuit divers that have supramedullary airways, the common murre and the Brandt's cormorant. So for the moment, we're not going to put forth a functional hypothesis to explain the presence or absence of supramedullary airways, and we can only say that this appears to be a structure for which the presence or absence of this structure has very strong phylogenetic signal. At this time, I would like to describe some of the variations in morphology that we have observed in supramedullary airways. You'll be seeing these 2 diagrams a lot in the next couple of slides. The one on top is a series of cervical vertebrae from an ostrich seen in dorsal view, and the lower one is anterior view of an ostrich cervical. This is what vertebral diverticula look like in a bird that lacks supramedullary airways. So here we're only seeing the intertransverse canals. And you can see also in that lower diagram that in the cervicals, they're actually running through the transverse canals with the vertebral artery, which is pretty cool. One variant we saw was where there were just small diverticular branches contacting the spinal cord at intervertebral joints. Sometimes these expand to enter the vertebral canal to a greater or lesser degree, but they don't merge with each other. So they're seen as discontinuous through consecutive vertebrae. In other instances, they did connect with each other. And then we would see these continuous tubes running through vertebrae that were articulating with each other. And the final, most elaborate morphology we observed was where there were continuous tubes through several consecutive vertebrae, and then these supramedullary diverticula were also connected with the supravertebral diverticula on top of the vertebral body. So it's just this elaborate anastomosing network of diverticula both around the outside and inside of the vertebrae. So here's a summary of all 4 of those morphologies. There's a couple really important things to note here. One is that this is really representative of a spectrum of morphologies. These all grade into each other, so they're not as discrete as they've been presented here. I just wanted to give you a sense of the variation that we see. And second, variation is extremely common. So between different taxa, we see different combinations of these morphologies. And even within a single individual, we usually don't see one single morphology. It's usually something like morphology C beginning anteriorly in the cervicals and grading into morphology B more posteriorly. Once we're seeing them inside of the spinal cord, we also had some common and rather unusual variants. A common variant is 2 paired tubes dorsal to the spinal cord, and that was what you saw illustrated in the diagrams I just showed. Another variant was 2 paired tubes lateral to the spinal cord. And sometimes these are almost ventral to the spinal cord as well. Sometimes, you saw this early in the talk when we saw the example in the ostrich, there are actually 3 tubes dorsal to the spinal cord instead of just 2. And getting even more weird, we saw one instance in the ostrich and one instance in the eclectus parrot where the spinal cord was completely jacketed by supramedullary airways. So the spinal cord is kind of floating inside of the vertebral canal, not contacting the bone at all inside of this airspace of the diverticula. Naturally, with all of this variation, we started to think about anything that might correlate with it and potentially cause and help us understand the variation. Originally, when we were just collecting all of our data and getting a gestalt feeling for it, we thought that size might explain some of the variation and that perhaps larger bodied birds had larger and more elaborate supramedullary airways. And we've already seen this in the ostrich and the pelican. However, the ostrich and the pelican, it turned out, just seemed to be outliers doing something kind of weird. And this scenario is much more common. So here we're seeing supramedullary airways in a bush tit, which is a really tiny, cute little songbird, compared to those in a turkey vulture, which is quite large. And you can see that the airways are a very similar size proportional to the spinal cord. And this ends up being the case regardless of body size. So we actually do not see that as an explanatory variable. We definitely did see variation occurring, a pattern of variation occurring across vertebral regions. So for all of the genera in which supramedullary diverticula are present, we do see them in the cervical vertebrae. And in nearly all of them, this is also where they are largest and have the most elaborate morphologies. Only about 60% of genera with supramedullary diverticula had them present in the dorsal vertebrae, and they start to become smaller here in general. And then they became quite rare by the time we got to the sacral vertebrae, and we only ever saw them in the very posterior-most sacrals. And about as rare in the caudal vertebrae. So by the time they're in the sacrals and the caudals, very rare and typically very, very tiny. So to summarize, we conclude that right now, based on our sampling, The presence or absence of supramedullary airways appears to have very strong phylogenetic signal. For every major clade for which we were able to sample more than one genus, all of the genera in a single clade either lack or possess supramedullary airways. Body size does not seem to be explaining the variation we're seeing in these structures, but moving forward, we plan to quantify relative volumes of the supramedullary airways as compared with the spinal cord. And vertebral region is a very strong explanatory variable, helping us understand the presence and absence and also relative size of these structures. Right now, we hypothesize this might be related to movement and function in that sense. So in areas of the vertebral column where we're getting lots of movement, in this case, the cervical vertebrae, we think maybe these supramedullary airways are a sort of cushion for the spinal cord as it's getting jostled around during all of that movement. And in more rigid portions of the body, they are less large and in some cases completely absent. So circling back around to my original definition of supramedullary airways, we conclude that they definitely are diverticula that branch from the lungs and the air sacs. But they don't occur exclusively inside of the vertebral canal. We also often see them at intervertebral joints. Nor are they exclusively above the spinal cord or supra to the spinal cord. Sometimes they are lateral to it, sometimes ventral, sometimes completely encircling it. Therefore, we suggest that a better term for these structures would be paramedullary airways because it's a bit more general. And we conclude that they are diverticula from the air sacs in lung that are occurring at intervertebral joints or inside of the canal and are generally in contact with the spinal cord in some way. And a final note, what's also really exciting about these structures, and my co-author Matt Wadle has reported on this at a previous SVPCA meeting, is that they leave behind osteological correlates quite regularly, which is super exciting because it means we can find evidence of these structures in extinct animals. Sometimes this is in the form of foramina in the the top of the vertebral canal, so they're pneumatizing the vertebral arch. Sometimes it's in the form of sculpting or fossae. And we've even seen foramina in the floor of the vertebral canal, where these diverticula are pneumatizing the vertebral body itself. Evidence of these osteological correlates has already been reported in several sauropod dinosaurs, so we know that some sauropods had supramedullary, or rather paramedullary diverticula of a sort. And of course, now we're quite curious to know whether other groups of archosaurs with elaborate pneumaticity might have had these structures as well. And very recently, just a couple of weeks ago, because Matt and I have been going around waxing so enthusiastic about supramedullary airways to our colleagues, we actually inspired Dave Hone to take a closer look at some pteranodon vertebrae, and he noticed foramina in the floor of the vertebral canals of this pteranodon. So that's super cool because now we're starting to see evidence of supramedullary or paramedullary diverticula in a pterosaur. And it's also cool because if it's in the floor of the vertebral canal, that means that we're either seeing in pteranodon the weirdest structure that we saw in birds, where the spinal cord was completely jacketed, or a case where they're only located ventral to the spinal cord. So that's super exciting as well. I hope I have piqued everyone's interest enough in this to make you want to all go out and peer inside of vertebral canals and look for foramina and sculpting. Please let Matt and I know if you find anything. Thank you so much for your attention, and now I'm happy to take any questions.